All right, in this lesson I want to talk about two applications of Ampere's law that we have that are fairly common applications that we might want to do. The first one is, what if we had some sort of cylindrical conductor that we could pass current through the whole volume of the conductor? So in this case, we're looking at the magnetic field inside of one of these types of conductors where the current goes through. So we're looking at two different regions, both the region outside of this conductor, but also the region inside of this conductor. So for all areas outside the conductor, determining the I enclosed is pretty easy. It's whatever the total current of the conductor is. I would still have a cylindrical Amperian loop. 2 pi r would be its distance. So B times 2 pi r equals mu naught times I enclosed. Well, I enclosed is just the current of the wire. And so we get normally what we'd find is the magnetic field from a long straight wire. So if you're standing outside of the wire, it doesn't matter whether it's a really thick wire or a really thin wire. The magnetic field always looks like mu naught current in the wire divided by 2 pi r, where the r is the distance between you and the center of the wire. Now if we look at inside the wire, what we need to do is define a new term to talk about current enclosed, and that term is J, which I would call current density. Basically, how much current is there per unit of area in this wire? So if you look at this and you look at the area as the cross-sectional area of the wire, what J really describes is what is the density of current on that area. How much current goes through each one of a little chunk of area. Well, to calculate the current density, it's pretty easy. It's just I divided by pi r squared, where big R is the width of the wire itself. The area enclosed is just pi little r squared, where little r squared is the area of the loop that I've enclosed. So this means is for the current enclosed, it really looks like I little r squared divided by big R squared, because the pi's cancel themselves out. This looks really similar to when we did Gauss's law, looking at the electric field inside of a spherical insulating material with uniform charge density. It's in fact exactly the same question. And so if we plug that into our equation for Ampere's law and do some math, we get that this is our expression for magnetic field inside of this conductor. That it increases linearly as radius increases, and then it looks like an inverse function once you get outside of the material. The second application that I have to do is to look at the magnetic field of a solenoid. So what a solenoid essentially is it's a series of cylindrical loops of wire that are close together. So think of taking like a slinky, particularly a metal slinky, and putting current through it and stretching the slinky out a little bit. So the individual loops of the slinky don't touch each other, but you have this kind of cylindrical loops of wire that make up the slinky. What's true about a solenoid is the magnetic field inside of a solenoid is pretty close to constant. This is similar to when you looked at a capacitor. The electric field between the parallel plates of a capacitor is close to constant. That makes solenoids very nice ways to produce uniform magnetic fields. So solenoids are actually very common, whether you know it or not. They're used to make up most types of electromagnets. They're used in transformers. So if you were taking power that was, or electrical energy that was at, say, 100,000 volts, and you wanted it to be at 1,000 volts, you'd use a transformer in order to step down the voltage. And as odd as this will sound, they're also used in the production of energy. We also find solenoids when we look at most types of electric motors as well. So let's look at how a solenoid works. So here I have a picture, or a couple pictures of a solenoid. Here I have the loops of my wire spread out. They all have current which moves, well, in a fashion that looks like it goes from the bottom of that page up. And so the magnetic field, if we use the right-hand rule inside, is going to be toward the left. In this case, we have electric current going in on the top, electric current coming out on the bottom. And so if you do that trick, you should get a magnetic field that goes left to right, or right to left, inside of that solenoid. So the integration path that we're going to use for an Amperian loop is really this integration path. Thing to point out with the perfect solenoid is the magnetic field outside the solenoid is really close to zero. So if we do our Amperian loop, B dot dl equals mu naught times I enclosed, what I could say is that B dot dl really equals just B times L, where L is the length of the solenoid I've enclosed. Now we can make some arguments for that. One is there's no magnetic field between points C and D, so B dot dl must be 0 because 0 dot dl is 0. Between either B and C or A and D, sure, there is some magnetic field in some of that region, but it's perpendicular to the direction of your loop. And so B dot dl would always be 0 because the vectors are perpendicular to one another. So the only one where there'd be any magnetic field is from A to B. B dot dl is equal to just B times L. So that makes our life a little bit easy. B times L. And that's going to be equal to mu naught times I enclosed. So how do we know what the current enclosed is? Well, the current enclosed is going to be the number of loops of wire, which I'm going to call N, times I, the current in each loop of wire. So if there are 100 loops of wire enclosed and each loop of wire contains 2 amps of current, you've enclosed 200 amps of current with that loop. So then we get the expression B times L is equal to mu naught, number of loops times I. So I could actually calculate the magnetic field of a solenoid by doing this. Say, I know the number of loops, capital N, I know the length of the solenoid L, I know the current in the solenoid I could calculate the magnetic field inside of this perfect solenoid. You'll sometimes see it written this way, mu naught little n I, where little n is defined as the number of loops per unit of length. So you sometimes will find the magnetic field of solenoid, and probably more frequently I write it out that way, where little n talks about the number of loops per unit of length for the solenoid. So that's kind of a quick overview of a couple of applications of Ampere's law and how we can use it to find some magnetic fields of some common situations.